Pleased to be here today, and thanks for the invite to give this talk.
Yes, thanks. Thanks for having us.
So today we're going to be talking about some work primarily that we did for NeurIPS 2020. The paper that we will be basing this talk on is called Identifying Causal-Effect Inference Failure with Uncertainty-Aware Models. This is joint work by Soren and I. And supervised by Uri Shalit at the Technion and our supervisor, Jaren Gao. So the structure of the talk today is going to follow three parts. So in the first part, I'll do a bit of background on personalized decision-making, applications to healthcare, how do we learn causal effects from observational data, what is observational data, using causal effect estimates in decision-making, and when we should trust those decisions. A little bit of background on Bayesian deep learning as well. And then we'll pass it on to Soren to go over methods and how we sort of took a Bayesian deep learning approach to address some of the issues with identifying treatment effects. And then we'll finish that up with some follow-up work that we've worked on. So without further ado, let's start by getting into personalized decision-making. I was having a little bit of issues with connectivity yesterday. Maybe Soren, give me a wave if things start lagging again or anything like that. So personalized decision-making is sort of concerned with the types of questions like, should I take an ibuprofen or hydrate to relieve my headache? Should I brake or turn to avoid an incident? Or should I study engineering or computer science machine learning? In general, there may be population level trends that will help one make these decisions. For example, maybe on the whole, it is better to take ibuprofen, maybe it's better to brake, or maybe it's better to study engineering. None of these options are scientifically validated. But what we're interested in with respect to personalized decision-making is specifically the best choice for you often depends on you and your environment. So what are these environmental factors, or what are the characteristics about you that are going to make that decision the best choice for you? For example, if you are a professional driver and you find yourself in a situation where you are about to avoid an accident, maybe it makes more sense to turn to avoid that accident. But if in your environment there is a pedestrian, then turning might be the wrong choice and you might want to brake instead. Before we go on, some interesting reading that I find that really explores sort of the problematic aspects of making decisions on behalf of others or for others based on data that is biased to a population that doesn't represent them, or invisible women, and algorithms of oppression. Interesting work that I would recommend following up on. So now let's take a second to look at, we're going to focus a little bit at moving from personalized decision-making in general to sort of the healthcare example to motivate our talk today. So I'm having a real trouble switching slides. Okay. Just have to wait for it. So I'm sure many of you have heard a lot of buzzwords these days: personalized healthcare, precision medicine, precision healthcare, targeted treatments, all of these things. And this is really focusing on how you as an individual are going to respond to a given treatment. Right now, sort of research in this area and even development of solutions is sort of being driven by the increasing accessibility of large-scale clinical data. So things like the UK Biobank, for example, where you have like 500,000 individuals. For a subset of those individuals, you have imaging data from brain imaging or from retinal imaging. You have genetic data. You have clinical variables. All of these sorts of things where you want to sort of learn about maybe causal mechanisms with respect to some given outcome. Of course, machine learning, something that shines when we have this data access, and really spurring a lot of work towards sort of learning from this data. There are some challenges associated with learning from this data because a lot of these data sets are observational. So they are collected from individual medical centers, like the UK Biobank, or they can be collected directly from you, say via a wearable smartwatch or device. Sorry. So what exactly do we mean when we say observational data? And so let's take a second to sort of go into that. I don't know why my slides are so laggy. Okay, so observational data is typically made up of so yeah, there's three sort of aspects to an observational data set. Right now on the right, we're just going to sort of look at a 1D example for illustrative purposes, but we have sort of these high dimensional covariates. These are descriptors of you. So this can be imaging, electronic health records, your genetic profile, various different things. Then we also sort of look at, we're sort of focusing on this case where we're looking at binary treatment. So individuals in this observational data set for which we have measured covariates also have a treatment that would be assigned after the variable has been measured. So that's a binary treatment here, which sort of partitions individuals into the control group, those who didn't receive treatment, and the treated group, those that did receive treatment. Then the outcome, for example, years survived after chemotherapy treatment, can be recorded after the treatment is administered. A fundamental difference. So a lot of this might be recap after Brady Neal's talk yesterday. But so he probably brought up maybe randomized controlled trials or experimental data, as well as observational data. So just as a recap, a fundamental difference between observational data and experimental data for randomized controlled trials, is that the treatment assignment, whether or not you belong to the treated group or the controlled group, is typically not random for observational data. So in that case, we are going to see associations between the covariate and the treatment. Here we see as the covariate value increases, we have a greater propensity, a greater probability that an individual will be assigned to the treated case. And also sort of relationships between the covariate value and the outcome. So as we have this trend, this very clear trend between the covariate value and the outcome. When you have a covariate that sort of satisfies these two properties, causal links between the outcome and the treatment, we call such covariates confounders. And if we want to learn something about causal effects in this model, we need to control for these confounders. So what can we learn then from observational data with respect to making personalized decisions? So the causal estimate of interest, when we're talking about personalized decision-making or individualized treatment effects, is the conditional average treatment effect. And so this CATE, the CATE is defined as this expected difference in potential outcomes at a measured covariate value. So let's take a second to sort of break down this equation. Conditional average treatment effect. So let's look at treatment effect. This is sort of the difference between potential outcomes. Potential outcomes are these causal quantities, sort of reflecting how would you respond to treatment were you treated, so Y1, or how would you respond to treatment were you not treated, Y0. So that's treatment effect, average. We're taking an expectation of this difference between the two potential outcomes. And conditional, this average is conditioned on some measured values, some representation of you. I hope that is clear. So how do we use the CATE for personalized decision-making, or how can this be used for, in an ideal situation, for personalized decision-making? So a simplified treatment policy would be just to treat an individual if and only if their CATE is positive. So if the treatment effect, given their covariate value, is greater than 0, we say treat. Otherwise, do not treat. So equivalently, we can say don't treat if and only if the CATE is negative. But what if we can't identify the CATE? What are some reasons why we wouldn't be able to sort of know about this CATE and learn it from observational data? So as I said, the potential outcomes are these causal quantities. And as these causal quantities, their difference is unobservable. In effect, I can only observe one of these two potential outcomes, the potential actual treatment that was assigned to this individual. So it is desirable then, or it's necessary really, to express CATE in statistical terms, where we move from these cost estimator for the CATE, which is going to be an expectation of an outcome, the observed outcome that we see, or the distribution of the observed outcome, the distribution of the observed outcome for each covariate value X. So if we look at sort of a non-parametric approach to this, we can get these conditional averages or conditional expectations. One for the treated group, where we get this line, purple line, that's just the mean of these treated group values. One for the control group, which is the blue line here, which is the mean of the observed outcomes. And this gives us our treatment effect in purple, which is just the difference between these two expected outcomes. However, the CATE estimator is not, or the CATE is not identifiable through the statistical estimator without further assumptions. So we have to assume that consistency, that our observed outcome, Y, is actually corresponding to the potential outcome of the assigned treatment. We have to assume, so as we talked about earlier, about the fact that observational data is confounded, we need to include all of those confounding variables such that our potential outcomes are independent of the treatment when conditioned on those confounding variables. If they're not, if all confounding variables are not included, this can result in a biased CATE estimate. And finally, which is going to be sort of the focus of this talk moving on, the overlap assumption, which is that for any measured value of X, our propensity for treatment, whether that treatment be controlled or treated, is going to be greater than 0 or greater than epsilon in a relaxed case. So I think we can already sort of get a sense at looking at this figure that if any of these assumptions are viable, well, what can we say about the CATE? I think we should be uncertain about the CATE. So in this image to the right now, in these blue boxes, we sort of are highlighting these regions where overlap is not satisfied, where, for example, we only see controlled examples on the left-hand side of the figure, and we only see treated examples on the right-hand side of the figure. So how can we calculate that difference in expectations? So now let's talk about Bayesian deep learning. So this is a way. Let's just take a second here. So parametric models can estimate statistical quantities. So let's just focus on the treated case here. So the expectation of the outcome, given that we observe treatment equals 1 and our measured covariate value X. So here on the right-hand side, we're seeing just the statistical mean of the observed data points, a non-parametric estimate. So neural networks, the weights of a neural network are induce a function that estimates the expected conditional outcome. So this expected conditional outcome, estimates the expected conditional outcome. And this function that is induced will extrapolate beyond that data manifold. So it gives us a sort of continuous function of our conditional mean in this case that will extrapolate beyond the data. If we use a maximum likelihood approach to learning these weights, then we get one functional explanation. But a question becomes, what should this function look like when we extrapolate outside of the support of the training data? And now we can turn to sort of a Bayesian deep learning approach to instead model a distribution over such functions. So instead of having one functional explanation of we have multiple functional explanations of the data that would each ideally explain the observed data equally well, and give us the opportunity to, when we extrapolate beyond the support of the data, so they agree with each other when they're on the support of the data, but when we're extrapolating beyond the support of the data, they ideally should disagree with one another. So that measure of disagreement or epistemic, that we can express our knowledge or lack of knowledge about covariate values through measuring sort of how much the functions disagree with each other at a given covariate value X. And we call this, well, in the literature, it's called epistemic uncertainty, how much the functions disagree with one another. Become more uncertain the more they disagree. We can also sort of think of this in terms of a classification problem, which I think is going to maybe be more intuitive for the next section. So we can have, instead of doing a regression problem in the last example, we can just have an observational data set where the outcome is health improved, health did not improve, which we can see here. Again, we can learn a function to predict that. A Bayesian model learns a distribution over such functions. On the training data manifold, those functions agree with one another. Off the training data manifold, they do not agree with one another. And we need this measure of epistemic uncertainty, which measures how much they disagree with one another. And we can use that measure then to sort of tell whether we are predicting for a data point, a new data point that lies within the data that we've observed, within the support of the training data, or if it lies outside of that training data support. So now I will pass that on to Søren to talk about the methods.
All right. Yeah, thanks for the first part. So I'm just going to go through some of the main ideas and leave out some of the extra details that you can find in the paper. Yeah, let's go on and continue with this example Andrew just introduced. Except now we have two graphs here. We're going back to the causal setting, where we have on the top the untreated control group, and on the bottom the treated treatment group. And each of these dots or circles, of course, represents a data point. So, and the sort of the line going through them represents the ground truth function, which gives the probability that a given point will have a positive outcome or an outcome of 0, 1 or 0. So in this example, we've designed it so that overlap is satisfied. There's no problem because for every sort of treated point, we also have untreated points close to it. And for every untreated point, we have treated points close to it, so that everywhere where the data set has coverage, overlap is satisfied. Next slide. But now we've shifted the data a little bit along the x-axis to create a situation where overlap is violated in this red area. So you can see in this area, you only have untreated individuals and no treated individuals. So it's obvious that we cannot really know what the Kate would be for these individuals. Now, as Andrew sort of talked about, with standard methods, if we estimate a function with maximum likelihood, we would just that function would just extrapolate in some way and then give us an answer about the Kate anyway, without highlighting to the user that maybe this answer is unlikely to be correct in this area. Next slide. Now, when we instead take this Bayesian deep learning approach, fitting Bayesian models to each of the groups, then we can see that this recognizes the data problem we have here. Starting first, next slide, with the region on the right. So this is not yet, I'll get to overlap in a second. This is not the no overlap region. This is just a covariate shift region, because we don't have data available for neither the control group nor the treatment group in this area. And so obviously we can't know what the Kate should be here, unless we would be unrealistically good at extrapolating. So yeah, in the bottom graph, we've sort of quantified, given a measure of this disagreement between functions that are compatible with the overall data. I'll give that in sort of quantitative terms later, but what you can see is the purple line at the bottom, that's epistemic uncertainty, the disagreement for the treatment group. The green line at the bottom is uncertainty for that one's for the treatment group. And then the black line quantifies the uncertainty in the difference on the expected outcomes, which is the Kate. So we can see that here's this sort of gracefully deals with this data problem we have in this area. Now let's move on to the no overlap area. You can see here that it also, this functional disagreement through Bayesian method also recognizes the uncertainty here. So yes, for the untreated group, we do have agreement between functions, so there's not much uncertainty. But for the treatment group in the middle graph, we lack the data. We have an overlap problem, and by illustrating this way, you can sort of see that the overlap problem we have here can be thought of as a covariate problem, but it's only a covariate shift for the green for the treatment group in the middle, so that we want to argue partly with this paper that you can just bring to bear the whole suite of methods that exists for addressing covariate shift problems and apply them to this overlap problem, because that's a covariate shift problem in disguise. Let's go to the next one. Right, so in this area, we can now quantify epistemic uncertainty in the Kate. And what do we do with that? Well, we can use it to define a policy for when we withhold or defer automatic treatment recommendation, because there's insufficient knowledge about an individual. Next slide. Right, so let's actually quantify this epistemic uncertainty. So recall that the Kate is the expectation of y1 minus y0. Now, to quantify uncertainty, we look at the variance of y1 minus y0. And we decompose that just to show the connection between the different sources of uncertainty that are at play here. So on the left side of the equation, I've written out the variance of y1 minus y0. And you can see that this, at the bottom, you see this probability. You can see that there are 4 sources of uncertainty. first parameters, omega 0, omega 1. And the second one, uncertainty about the potential outcomes, y0 and y1. So the sort of Bayesian approach brings in this uncertainty about the parameter. Sort of normal, some likelihood approach. Now we can decompose this whole variance on the left. You can see that the term at the bottom is actually the one we care about. So this is, we wanted to indicate, and you can see that it's mu0. This is just our estimate of the Kate. And so this term is really quantifying the thing we care about, which is uncertainty in the Kate. And this is an epistemic uncertainty. We call it that because it's a lack of knowledge, meaning it can be resolved with seeing more data. So if we were to see a lot of data in all the regions of the input space, then this uncertainty would dissolve. That's what makes it an epistemic uncertainty. The other term at the top, that's what we call, it cannot be resolved through seeing lots of data. That's why we call it aleatoric uncertainty, coming from dice in Greek, meaning the throw of a dice. You can never predict what the dice will come up with, even if you've seen a million dice rolls before. And luckily, it turns out we can ignore this uncertainty because we are only interested in the Kate, which is the expectation over the potential outcomes y1 and y0. So the inherent stochasticity in y1 and y0 can be ignored because we are taking the expectation over them. And this is handy because it's actually impossible to quantify this aleatoric uncertainty term, because it would require us to both observe both potential outcomes, y1 and y0 for the same individual at the same time, which is impossible because you can only ever treat them or not treat them. But this luckily factors out. So we're going to use this term at the bottom, variance of the Kate, going forward to defer decisions. So let's go to the next slide. Right, so given that we have this epistemic uncertainty, how do we decide which points to defer? Well, in principle, when the Kate uncertainty exceeds some threshold, recommending a treatment would be unsafe. So how do we set the threshold in practice? There are two sort of main ways to do that. One is it can just be given by medical authorities. So for example, for tasks like diabetic retinopathy, there will be usually in many countries a medical authority that says your probability of false positive should not be above such and such. Your probability of a false negative should not be above such and such. And you can work backwards from there to set the right threshold of the epistemic uncertainty. And the second way to do it is to set a threshold is to use a domain expert who can put cost values on false positives and false negatives. For example, in treatment of COVID, I'm not an expert, but as far as I know, people are often given antibiotics in the ICU because COVID patients also tend to acquire a bacterial pneumonia. And antibiotics are given because there's not that much harm to giving them. They usually don't kill people, but not giving them when somebody actually has a bacterial infection, that can kill them. So the cost of a false the cost of treating someone that doesn't need to be treated here is much lower than the cost of not treating someone that would need the treatment. And so again, from these costs, you can work backward to set a threshold on when you should defer points for sort of expert evaluation, because we can't trust our automatic system. This is sort of our approach. I also say that sort of existing methods usually don't use epistemic uncertainty, but instead use the propensity score. So recall that the propensity score is the probability of treatment for a given individual. So, high propensity means that this individual is very likely to be treated. And we can defer points because they have byte overlap assumption when they have a very high propensity, close to 100% or close to 0, very low. Next slide. Cool. So let's get into some results. So because there aren't that many really high-dimensional data sets weren't in the causal inference yet, we started by designing a benchmark, which is based on the MNIST data sets, which is very common in machine learning. It's this classification of handwritten digits. And we adapted it for our purposes to turn it into a causal inference task. And on this left graph, we sort of illustrated some of the problems that the propensity-based deferral approach runs into, which are handled more gracefully by epistemic uncertainty-based deferral. So click, please. So this is a propensity histogram. On the x-axis, we have, propensity. On the y-axis, we have how many individuals have that propensity. And in this area on the left, we sort of used one digit of the MNIST data set. I think it's the digit 9, where we have loads of data, as you can see by the high big hump. But they have a pretty low propensity. So most of them are blue, they're not treated. So the propensity-based rejection method would sort of defer these points because the propensity is very low. But actually, what it doesn't take into account is that we have loads of data here. So despite the low propensity, we can still estimate the Kate because we have so much, we still have like a good number of treated individuals, even though most of them are not treated. And this gives us low epistemic uncertainty, so we're not going to, distrust our model here. Next one, double click. Yes, so this middle region, these are where most of the sort of digits lie. And they have this middle trending nice 0.5 propensity. So our propensity-based methods will definitely like these points and assume that we know the outcome, that we know the Kate here. But actually, here we have very little data. So we shouldn't actually be able to know the Kate. So you can't see that in this histogram because it's a whole bunch of different classes, image classes, put into this one region of the histogram. But actually, each of those classes has very little data. So the Kate is very uncertain. And that's what epistemic uncertainty quantifies. And then finally, we have a third region, double click again, where the propensity is actually 0. The propensity is 100%. All the individuals are treated. And here we really can't know the Kate, and we're going to see that both epistemic uncertainty recognizes that because it recognizes the covariance shift for the control group. And of course, the propensity methods also work well here. Moving on to the graph on the right, these are just results in terms of accuracy. So we have number of errors, and we see on this data set, withholding points with epistemic uncertainty as the green line achieves a much lower error rate than propensity-based methods. And in fact, the propensity-based methods do somewhat worse than random, which may be surprising, but it makes sense if you look at if you're aware of the problems that I just pointed out there with the propensity method. Now let's move on to some of the standard causal inference-based benchmarks. So these are IHGP and ASIC that we use here. IHGP is sort of probably the most well-known one in causal inference. And we see the exact same pattern here. Each time the green line, the epistemic uncertainty, gets a much lower error. And we've, oh, by the way, I should have said on the x-axis, we're sort of sweeping over how many points we differ. So, for example, in the left graph at 40%, if we can see if we defer the 40% points with the highest epistemic K uncertainty, then we've basically reduced the error on the remaining points to almost 0. So this sort of goes to show how common sort of problems like overlap and covariate shift, probably mostly overlap, are even in a very nice curated data set like IHGP. It is still the case that we can achieve much lower errors by letting the automatic system do the points where the automatic system knows what it's doing, and then leaving the other points for maybe an expert or a different system that is not so personalized. And on the middle graph, we've designed a variant of IHGP that has covariate shift. Again, you can see here that the uncertainty-based method still works. And then finally, it also works the best on the ASIC data set on the right. The benefit is a bit less extreme here, but there's a clear improvement in the error from rejection or withholding with epistemic uncertainty. Next, please. These results that I just showed, we're just replicating them across a whole bunch of different, at the time, state-of-the-art causal inference models. So models like DragonNet, HARNet, T-Learner, and these are all deep learning methods except the top one, which is Bayesian additive regression trees. And you can see across all of the methods and all of the data sets, uncertainty-based deferral does better than propensity-based methods and random deferral. All right, that was my part. I think maybe we can. You want to do some more slides, Andrew, right? So we can skip this one.
Oh, you don't want to just conclude this bit?
All right, let's do it. I hope we have enough time. Yeah, so I'll just briefly conclude. Observational data, especially when it's high dimensional, often violates the overlap assumption. And additionally, treatment recommendation is made for individuals who are different from the training data, for example, because the training data comes from some region or hospital. And this is called a covariate shift. A good causal model should communicate both of these problems to the user. And for both of them, epistemic K uncertainty provides a unified approach to identify these failures by keeping a Bayesian posterior over the weights of our model. Did you want to take it over from here, Andrew?
Sure. Thank you very much for that part, Soren. Also, I see that there are some really great questions in the chat. I'm just going to finish these last two sections on related work, and then I'd be really happy to get them. And if more people have questions, please submit them to the Q&A. So this work was really focused on sort of quantifying our uncertainty about conditional average treatment effects when the overlap assumption is violated or when we have experienced covariate shift. So in that case where we are very uncertain about a point, we're saying a deferral should be made. And this deferral can take many forms. If it's a very time-sensitive application, then maybe that's deferral to an expert. Maybe that's deferral to a safe policy. But if there's more time, maybe we can do better. Maybe we can learn more about those points that we don't have high certainty about. And one of sort of a follow-up direction that we took was looking at how can you reduce that uncertainty, and specifically at looking at reducing uncertainty due to non-overlap or to covariate shift. So this work was submitted to the Neglected Assumptions in Causal Inference Workshop at ICML in 2021. It's called Causal Bald, Deep Bayesian Active Learning of Outcomes to Infer Treatment Effects from Observations. It's a mouthful. This is a co-work with Panagiotis in our lab, as well as Joost van Amersfoort and Andrew Kirsch, and again, supervised by Yuri and Jaren. So this work really is focusing on how do we get a sample efficient strategy to acquire outcomes for observational data. So again, similar observational setup where we have our observed, we have our two groups are treated at a control. We want to get outcomes in those groups, and we have a pool set that is just consisted of covariates and assigned treatments. We want to acquire labels for those, and we want to sort of efficiently explore that pool set so that we're acquiring points that are going to be maximally informative about our treatment effect. So a very naive approach would just be to randomly acquire points. And this is interesting in a sense that randomly acquiring points from your pool set, examples of treated or untreated measured covariate values, will lead to this unbiased sample of the pool data, but that might not be what you want when you're looking for data efficiency, or even for finding being accurate across the data, because random sampling kind of biases the acquisition of your training set towards the modes of this distribution. So we get an unbiased sample of this pool data set, but if there already exists bias in that pool data set, then we're kind of amplifying that, or not amplifying it, but we're not mitigating that bias by doing random sampling. And as we can see, we sort of are very certain in the bottom pane of this graph, we're very certain around points near the mode of the data in the middle and accurate. But as we move from that mode, we become more uncertain about the treatment effect, the Kate, and actually less accurate about the Kate as well for a given number of acquired points. So we take instead an information theoretic approach to sort of efficiently explore regions of the pool data and focusing on those regions where overlap is satisfied, but also sampling points for which we're more uncertain about. So the points that are going to reduce our uncertainty the most, or result in a maximum information gain, which we sort of express as the information gain between our parametric estimator of the Kate and the observed outcome, or the observed potential outcome, the potential outcome that we can observe given that T has been assigned. So that's one sort of direction of work. This is a really active field of exploration. So we talked about the three assumptions: consistency, unconfoundedness, and overlap. So another assumption there was unconfoundedness. So how do we incorporate beliefs about hidden confounding in our Kate estimates? And this was work again with Soren and I that was accepted to ICML 2021, called Quantifying Ignorance and Individual Level Causal Effects Estimates Under Hidden Confounding, another mouthful title. And here we sort of looking at, in addition to incorporating uncertainty due to insufficient overlap into personalized decision making. So again, this is sort of looking at that first work, the work that we presented today, where we want to be uncertain when there's not overlap or there's covariate shift. We'd also like to incorporate whatever ignorance we might have about the treatment effect due to the possibility of hidden confounding. So as we can see here, hidden confounding, what hidden confounding does is induce a bias in our Kate estimate. If we have an X that affects both the treatment and the outcome, and it's not included in the model, this is going to bias our Kate estimate, showing a difference between the true Kate, the black dash line, and the predicted Kate. And this is something that epistemic uncertainty cannot reflect, this bias. This bias is not contained in epistemic uncertainty alone. The model will still be certain where there is a lot of examples in the data, and uncertain where there's not, but it doesn't say anything about this bias. So we sort of extend work by Angela Zhao, Nathan Callis, and others to make sort of a scalable, unified approach to model both our uncertainty that arises due to our belief in hidden confounding using a causal sensitivity model, and this epistemic uncertainty to give us this Kate interval for which we can use so I guess I will stop there and we can take a look at the questions. Some very good questions. So Sarah asked earlier, what do you think of trans and non-binary people who have been mistreated by doctors over the years? And I think this is a really, really interesting question. And I think that's a very real problem. I'm not an expert on that. And I would really appreciate any reading material that you might have, but I think it's a terrible problem, and but I don't know if I can say anything intelligent about it right now, because I'm unfortunately not very read up on all the problems that exist. So maybe I can pass this one to you, Soren. Dimitri asks, could you please elaborate on epistemic and aleatoric uncertainties and how they connect to overlap and underconfoundedness assumptions?
Yeah, sure. Maybe we can go back to the math slide. Well, let me first of all maybe define the aleatoric uncertainty a bit better than I did before. So if you look at the first term on the right-hand side here, what we have is, and especially the y1 minus y0 part, right? So what where the variance here comes from is that the outcome for any given patient is not deterministic, or at least it's not modeled as deterministic. So even though we've conditioned on knowing the parameters, right? You can see here we're conditioning on mu parameter 1, mu parameter 0. Even though we sort of assume that we know the ground truth function, there's still some uncertainty in the actual outcome, because there's some stochasticity in how people actually respond. So you can only basically know the expectation of the response, not the actual response for any individual. So that's why we call it aleatoric. It's like inherently stochastic, and we cannot learn it even with infinite data. So this uncertainty, I would say it's not so much related to overlap, and that's lucky for us, because it means we don't have to model it. What is related to overlap is the epistemic uncertainty. That's the one at the bottom, and that stems from uncertainty about the true parameters that generate the outcome distribution. And yeah, I guess going back to what I said earlier, when we have an overlap problem, we're going to get some epistemic uncertainty. So specifically, let's say the overlap problem we have is the treat that for a given sort of set of covariates or a given point at the x-axis, we've seen a bunch of treated individuals with these characteristics. Or let's give an example actually. Let's say, you know, we have a covariate that says, you know, whether somebody is pregnant. And now we have a pregnant woman in our praxis, and we want to sort of make a personalized treatment decision. Now, as it's probably the case that that in our training data, we've never seen a treated pregnant woman, because for a lot of different treatments, there's just a general like consensus not to give them to pregnant women because we don't know the consequences for the child, especially. So we've probably never seen how this treatment works on a pregnant woman. But if we just use a likelihood-based or maximum likelihood-based model, it will probably have some confident answer about what the outcome will be. And so, you know, we're going to get, if we use epistemic uncertainty here, we're going to have this parameter uncertainty, which tells us that for the treatment group, we don't know basically how this pregnant woman will respond to treatment. So that'll give us some like different possible outcomes, and then we have epistemic uncertainty in the treatment in Y1 basically, or in the expectation of Y1. So how do we relate to unconfoundedness? That was, I think, a different part of the question. And well, I guess it's I'm not sure if this is a solved question. We've been working on it a bit. Maybe Andrew can also chime in here. Because we have sort of tried to quantify or try to conceptualize really better uncertainty that stems from confoundedness. So when there is a confounder that is not part of X, one that's unobserved, that should give us some sort of additional uncertainty in the treatment effect. But this uncertainty is, I think, not very well understood how to model it. And I guess I would say it's different from epistemic uncertainty, and it's different from aleatoric uncertainty. Although, I mean, it's a bit of a semantic question, because you could define aleatoric uncertainty as including uncertainty that stems from not seeing all confounders, because, you know, this is also confoundedness is also a problem that stems from that cannot be solved by seeing lots of data, or you need to, so that sort of fits the aleatoric uncertainty concept of that a bit. But, you know, whether this aleatoric uncertainty or not is, I would say, essentially a philosophical question. Yeah. Do you have anything to add?
Yeah. I mean, we've definitely been thinking about this a lot, and it's a really interesting question. How aleatoric uncertainty, well, what uncertainty relates to sort of hidden confounding. And I think that, so there will be a component of the aleatoric uncertainty that in Y, in the outcome itself, in our ability to predict the outcome, stochasticity in the outcome, that will be due to an unmodeled variable, due to model misspecification. The tricky bit is, well, one of the tricky bits is, how do you know if that is coming from a hidden confounder or not? And so there's a very interesting and conceptually challenging sort of relationship between the how this is affecting uncertainty in both our treatment assignment and outcome, but I don't totally understand it yet. And there is the fundamental problem of the other part that's very difficult, is just we don't observe the difference in potential outcomes. So we can't really, without further assumptions, we can't say anything really about the variance of Y1 minus Y0. Like you could take a very, you could take a very wide wide bound on that uncertainty and say y1 and y0 are independent, so I can just use a sum plus of these two uncertainties to say this is going to be my range due to possible hidden confounding, but that's a very, very wide bound. That's basically the worst case assumption. Because we don't observe that difference, we can't really model that interaction. Maybe we can move on to another question. So that was from Dimitri. So Oksas, sorry if I'm mispronouncing your name. Let's assume that you have two hospitals that don't want to reveal their data and do their own Kate modeling. Would it be possible to combine two separate Kate estimates into a single unified Kate estimate? I think that's a really interesting question as well. So I know that there is some work, and I wish I had direct citations there, that looks at modeling our uncertainty in the Kate using sort of a bootstrap method where you would train individual models on bootstrap samples of the data. So I feel like that's kind of akin to having different hospitals and then maybe doing some sort of model averaging over that. I think there are probably a lot of issues that maybe I haven't fully thought out of some failure modes there. But Soren, do you have any further thoughts on that question?
Yeah, I mean, it's actually a very interesting question. I mean, it very much sounds like a differential privacy question. So maybe, maybe this is actually an interesting idea for a paper to extend differential privacy methods to the sort of setting where we're trying to train a Bayesian model. So I think in differential privacy, you would basically have this kind of question where you're trying to train a model on, different private data sets without sort of having to share those data sets between like different parties. And then at the end, it seems to be possible to get out a model. Maybe you pass the model around to the different stakeholders or so, or maybe like you share a sort of anonymized version of the data set where you add a bunch of noise to the data. And then you train a model on that anonymized or noisy data set. But yeah, I'm not sure if it's possible yet to do that while also preserving good uncertainty estimates using some Bayesian deep learning approaches. So that would be actually pretty interesting. And if not, then maybe somebody should do it.
Cool. And we have a question from Dimitri. So if we go back, could you please go over some data sets used for causal inference benchmarks? Are there ImageNet kind of data sets for causal inference? I suppose the best data set would be a data set from an actual RTC, perhaps. If we go back to this slide here, I think that there was interesting work recently. Okay, so first of all, we sort of showed a few examples there. So IHDP is definitely one. This ASIC 2016 data set is definitely one. There's this jobs data set, which sort of uses, so not jobs, but there's a twins data set that uses twins to sort of have non-synthetically generated potential outcomes. So that's sort of one way to go around it. But there was a really interesting work at this neglected assumptions in causal inference workshop by Alicia Kurth, who's a student in Michaela van der Schaar's lab. I think it was called How Great Is Your Kate or something like that. And that is really, I would suggest reading that paper. It's sort of like going into the issues with benchmarking Kate. A lot of them that we're using are semi-synthetic, so the outcomes are generated. How does the inductive biases, that paper explores how the inductive biases of different models are going to cause differences in performance that may not be sort of genuine in benchmarking. would ideally RCT data be what we want to validate on? I'm not sure. Soren, do you have any thoughts on that?
I'm also not sure.
But hopefully that gets at your question. It's an interesting thing. I haven't really thought of whether or not RCT data would be the best to use for benchmarking. I could see potential problems with it if they're small sample size. Could very quickly overfit to those data sets. I really have to think about it more. Jeff, do we have till sorry, I'm in Eastern.
Yes, we have still a few more minutes. We have 5 more minutes until the break, and then we're going to a 10-minute break after that.
Okay. From Dimitri, could you please describe on some of the other methods you had in the table, DragonNet, TARNet examples? So I can go back to that slide. So we looked at several different methods here. So BART was very standard Bayesian baseline that uses Bayesian additive regression trees. It's not really well suited, let's say, for high dimensional data, large sample data, but it definitely a necessary baseline, given that we want to it can quantify epistemic uncertainty as a Bayesian method. Then we sort of looked at different, we made Bayesian versions of some of the state-of-the-art, let's say, neural network models at that time. So you have these classes of meta-learner, S-learner, T-learner, X-learner. We just looked at T-learner in that case, which is basically we took 2 neural networks and each would be trained on either the treated cohort or the untreated cohort, and you get the difference. And they're 2 Bayesian neural networks, and we would get a distribution over Kate by sort of taking the variance over the output predictions of those 2 networks, expected output predictions of those 2 networks. TARNet is a neural network approach that has sort of a feature extractor. And then after the feature extractor, it's similar to a T-learner where you have 2 branches of the neural network that are predicting for the treated and untreated group. Then we looked at an extension sort of TARNet, which is the counterfactual reasoning network, which has a penalty term on the intermediate representation to promote overlap between those 2 representations. So it will, where the TARNet doesn't have any constraint on the intermediate representation before you get the 2 heads of the network. This will say, I want the distributions of these I want the distribution for the intermediate representation of the 2 arms of the trial to overlap with one another. So there's something quite interesting here, that method did not do so good it did quite bad on the high dimensional data set, the way we set it up. And I think that some of the in high dimensions that can cause some digits to kind of overlap with each other that they shouldn't. So it kind of loses, it could make 2 different subsets if there is completely no overlap, kind of map to the same point, which might be problematic, but we didn't go too deep into that. So that's something that I think would be interesting to follow up on. DragonNet kind of does the opposite of CFRNet in that it has an intermediate representation that is also used as input to a linear regression, a logistic regression of the treatment effect. So it actually linearly separates the data of the intermediate representation. And finally, Bayesian CVE, which is an extension of CVE, which is a causal effect variational autoencoder, which is a method that is going to try to extract representations. So it treats X, we say X is going to be proxies for latent confounders, not totally unobserved confounders, but latent in the noisy proxies that we observe, and it will learn a representation of the latent confounders for which to have your model going from Y and T from those latent confounders. So hopefully that answers your question. There's lots of other models, but these are the ones that we focused on. So is the sorry.
Maybe in the interest of time, we probably should wrap up with the questions and carry on with the rest of the questions on Slack. So I see Soren already joined the Slack. So if you could join Slack, Andrew, that would be great. And then people could continue asking those questions to you there. But other than that, excellent presentation, and thank you so much.
Oh, thank you very much for having us.
Thank you.